Thank you. Good morning, everybody. So quantum computing and machine learning, friend or foe? It might be perceived as strange questions, as quantum computers are supposed to be exponentially faster than anybody or any other computer. But in fact, as we will see, it's not always the case, and there are some specific machine learning algorithms that cannot run on a quantum computer. So those are the main topics I'm going to cover this morning. So I'm going to start by a short overview about what's quantum computing. I don't know if everybody is fully knowledgeable on this topic, but so I'm going to start by running an interesting video which has been recorded by the most senior researchers in the quantum computer team within Microsoft Research. And it's like an advertising, but done by researchers. If you think about quantum, you might think about photon, electron, proton. So you might think about very, very small things. But in fact, if you look at a real tangible quantum computer, it's more like this one. So it's like a giant fridge. So it's not something very tiny. It's really big. And in fact, it operates at 15 millikelvin, which means that it's very hard to get the operating temperature in it. We need about 2 days in order to cool this environment. So our goal with this kind of computer is to solve a lot of problems, but also to raise some potentially new concerns, especially about privacy and security. About privacy and security, I think the reason for which quantum computing has been very famous is because of Peter Shor, who in 1994 invented a new algorithm where you can factor a very large number. This is a 2048-bit number, and the goal is to find 2 primes. When you multiply those 2 primes, you get this number. So on a standard computer, it takes a while. When I say a while, it's about 1 billion years. So it's a while. On a quantum computer, using Shor algorithm on 1 gigahertz quantum computer, you can get the same factorization operation to be accomplished in 100 seconds. So if you look at on 2 log scale curve, you get an idea about what's happening with a classical computer and what you can get with not too fast quantum computer. So it was the main reason for which the initial success, at least in the media, for quantum computer was raised. But hopefully, even if this one could potentially break the entire internet security, that's not the only goal of quantum computers, hopefully. So in order to better understand what's about in any quantum computer way of interacting, I think I need to go a little bit about some details about quantum mechanics. So perhaps you remember quantum mechanics was at first invented at the beginning of the 20th century by Max Planck. And in fact, he was stuck with a very classical problem nowadays, but at that time it was really very strange. It is the black body problem, where when you try to put a stove and to warm it up, according to the theory available at that time, you should generate not only normal temperature, but also you could potentially generate X-rays, which means that anytime you try to cook anything, you could get cancer. So fortunately, it was not the case, and it happened that if you are able to assume that energy is emitted and absorbed in discrete quanta of energy, you could potentially come to a model where this doesn't happen. So it was the initial idea. Then Einstein and de Broglie came with a way to generalize this approach with this wave-particle duality they introduced at that time. It was for Einstein the opportunity to introduce the photoelectric effect, which he invented. And in fact, you remember, I guess, from your training course, these interference patterns that could only be created due to this wave-particle duality. And I insist on that because when you use a quantum computer, what you have to do basically is to use interference patterns in order to potentially reinforce an algorithm path in order to make sure that the algorithm goes into the right direction, while at the same time you could potentially make sure that some waves are in phase opposition in order to cancel this path in the algorithm. So this model was very efficient, at least for the first atom in the classification. So it worked very well for hydrogen. And in fact, it was the Bohr model, which was very efficient. But unfortunately, if you go from hydrogen to helium, it doesn't work at all. And in fact, at that time, 3 mathematicians came on board in order to try to invent something new in order to cope with this environment. And in fact, what they invented at that time was a mathematical formalism in order to abstract the quantum theory and make it work on any kind of atom. So they introduced quantum mechanics as just linear algebra. And in fact, quantum mechanics is just that, which implies that in order to be a good quantum computer scientist, you need to understand very well what linear algebra is. So the goal is to basically encode states of matter in a column vector, which comes from an I belt to the n space. You are able to measure state of matters by going through what physicists call wave function collapse, which is basically to measure a probability distribution. And in fact, the probability for phi to be in J position is just the square of the square of AG, which could be potentially imaginary. So in order to do any kind of transformation in a quantum computer, you have to use unitary matrices, which means that any kind of transformation is able to preserve vector lengths and probability distribution. That's what is, I think, the major thing we need to think about when you will talk a little bit later about machine learning. So let's go a little bit into what's quantum computing. So it has been mostly invented, even if Richard Feynman was not the only one. At that time, he tried to simulate on, it was, I think, IBM PC 386 at that time. He wanted to simulate physical systems. And he came very quickly to a very large problem, because if you have any particle with a spin and you want to simulate the interaction between 100 particles, you need to simulate a 2 to the 100 system and to consider a wave function where you have to the 100 dimensional. So it was not able to work, and in fact, even today, if you want to simulate such a system, even on the largest computer available in the world, it's not possible at all. So his solution was to build a computer that had, at the very bottom, the quantum properties directly built into the system. So it was his idea, which means that at the end of the day, quantum computing is essentially a machine which is able to simply rotate a quantum state vector on this sphere, which is to the n-dimensional sphere, which is usually named the block sphere. And the goal is to rotate this vector on this sphere in order to potentially do calculation. Anytime you try to measure the state of the system, you only get n classical bit of information. So the wave function collapses at that time, which means that you could have potentially a lot of computation that are going into parallel, but anytime you measure it, you just get a 0 or a 1 with a certain probability for one single qubit. So if you look at the very structure of any quantum algorithm, you first have to deal with input data. And as we will see, that's a major concern. Anytime we try to run on a very important set of data, because it's very hard to enter those data in any computer, and especially in a quantum computer. So, as an example, if you imagine that you have the MNIST set of data, which are a set of training vectors, and you want to enter those data into a quantum computer, you have to use this kind of calculation. So you convert the one, as an example, in a unitary vector, and you do the product by the first element of your state vector, then the second and the third one, and you divide by square root of n in order to preserve the probability of the environment. So it could potentially take a while, knowing that if you have to transform, then you have to manipulate this state vector and to change the position and to rotate the vector on the sphere. So in order to do so, you can potentially use what is usually the core of any quantum computer, which is to use some gates. There are some classical gates, like the NOT gates, the CNOT gates, the control NOT, which is the Toffoli gate. Those gates are, and this is very important to understand that, they are all reversible, which is not the case of standard gates in a classical computer. As an example, the AND gate is clearly not reversible. And in order to do measurement, this is something I will cover later, you also need to have some quantum operations using some specific gates, like, as an example, the first one, which is a very important one, the Hadamard gate, which is able to position any qubit in a superposition state. And that's usually the way you enter into the parallelized world. You have other gates, like the phase gates and the pi/8 gate, which are usually used in order to rotate the vector on the sphere. So using those set of gates, you can produce a universal computer using just a Toffoli gate, as an example, and a Hadamard gate. That's sufficient. Anything else could be done through those two gates. Then there is this measurement, which is something very weird, because this is the only nonlinear operation you do. And this referred to this Schrödinger's cat, which could be alive and dead at the same time until you open the box and get, with a certain probability, a cat which is dead or alive. So if you want to just apply this same logic to the MNIST data set in order to recognize characters, you have a probability to get a 1 or a 9 or any number depending on the number of data you've got in your data set at the beginning. So that's basically how it works. Very, very simplified. Now I'm going to switch a little bit on what could be done before having a quantum computer into our hands. This is what I call quantum-inspired optimization. And in fact, this is a very interesting topic, and it produced very interesting research and tangible results. So if you want to train a model, you can potentially have a classical input, use classical training using standard machine learning algorithm. You could also potentially use some kind of quantum training, which might happen not necessarily on a real quantum machine, but potentially on a classical one. And in fact, you could produce better quality algorithm using those quantum-enhanced training methods. And it will help you to produce a better classical model, but also, in the future, a better quantum model. So there are a lot of improvements that can be done using this environment. This is a map on what could potentially be done. If you look at the right hand, I suppose that you can have 1 million qubits. It's far away from what's available today, but that gives you a roadmap for what might be possible in the future if we have some scalable quantum computer at our hands. What's interesting is you can potentially use quantum effects in order to optimize algorithm on standard computers, like, as an example, using the tunnel effect. The tunnel effect is a consequence of the fact that you have this duality between particle and wave. If we had only particle, this couldn't happen in any case. But using this quantum tunneling, you can, as an example, the fact that it's very hard to find the global minimum using a classical computer, but it's much more efficient to use a quantum algorithm to do it using this tunnel effect. And in fact, this is something we have been doing in order to improve classical algorithm, in order to find better optimization methods, better model, and better training. And it has been used in order to help an automaker which was trying to solve traffic optimization in Beijing. So I just want to finish by giving you some ideas of what are the main goals of quantum machine learning. First, find new applications of quantum computers to machine learning. And in fact, using quantum computer, you can get quadratic and potentially exponential speed up depending on the algorithm you are using. If, as an example, you are using matrix multiplication in some part of your algorithm, you could get exponential speed up. But for other algorithms, like the one I was mentioning, deep learning, as an example, which is by nature non-linear, there is no chance you could ever run deep learning on a quantum computer. But you could potentially replace deep learning by a Boltzmann machine, as an example, which will give very good results on a quantum computer. Second, devise new methods to learn information about quantum systems, because it's very important also to potentially understand what's happening in the quantum world. And third, understand what are the fundamental limits physics place on learning. And that's a very interesting research topic on which I will not have time to spend because it's over. So my slides will be available. I have a bunch of other slides listing various machine learning models in order to give you some hints on how to use potentially those machine learning models as far as input, which is a concern, output, and potential speed up the algorithm will give you. This is a topic which is very interesting as far as research is concerned. So if you're interested, I encourage you to start working on quantum simulation. Those are available today. There are a lot of quantum programming languages available today, and that's a good opportunity to start, because if I believe in what I believe today, I think a real quantum computer which is able to run those kind of algorithms is not too far away. Thanks.